So let's start a little in chapter 5. We are skipping around a little in chapter 5, so we'll just do a couple of the sections. But 5.1 is the probability distributions. So the idea of you want the entire options for everything in a chart is a distribution. So you can see this first example here has a chart with number of heads when you flip two coins. You either get 0 heads, 1 head, or 2 heads when you flip the two coins, right? And the probabilities add to 1. So it shows all the possibilities and all the probabilities, and that is a probability distribution. Okay, so this first thing, random variable, it's just referring to like whatever those options are. So flipping a coin, heads, tails, um, it's usually a numerical value. So it would be the number of heads, the number of tails, not usually it is. Would be another example. It could be the number on a dice if you rolled a 6-sided dice. Then you could get a 1, 2, 3, 4, 5, 6, and then probabilities. So we'll see examples of them. But the random variable is literally referring to whatever you put here. Random variable. P is our probabilities. And the big thing when you do these probability distributions is it better add up to 1. This should say 2, 1. That's okay. And it's usually in a table and it better add up to 1. It doesn't have to be in a table. But if I say it's going to snow, the probability of snow is 20%, then the probability of not snow is 80%. So I could put those in a table. They add to 1 or 100%. So then that is a full probability distribution. It's just showing all the options. So the first couple questions literally say, is this a probability distribution? Add up your probabilities and they better equal 1. And these ones do. So 0.25 plus 0.5 plus 0.25 equals 1 or 100%, depending on what they have, percents or decimals. Usually it's decimals. So a bunch of your questions are literally, is this a probability distribution? Do they add to 1? So does it have all the options? Then we start to look at what is associated with probability variability. Nope, this is just showing adding them up to 1 and the value. So we could also look at a tree diagram for 2 coins. I like presenting some of our situations in a tree or a Venn diagram because sometimes you need those to be able to think through your options. So when I flip a coin, it's either heads or tails, and you have a half chance of the heads, half chance of the tails. Then if I flip again, it's the same way, half. And so you can see that to go heads, heads, right? Heads, it's 1/2 times 1/2 or 1/4 probability. Okay, to go heads, tails, it's the 1/4, right? Tails, heads is 1/4, and tails is 1/4. So there's 4 different options there. And so 1/4 for each one. And if we go back up here, this is 2 number of heads. There's one. I was circling the 2, but there's only one option for no heads and 2 heads. But the 1 head, you could see there's 2 options here. And that's why they added those together to get the 1/2 or the 50%, because there were 2 ways to get 1 head. Okay, so that's looking at a tree diagram to kind of help you with the probabilities and, another way to think about organizing your data. So is the following a probability distribution? What are we checking? Right? We're checking if these add to 1. So let's add these up. And I get 1.4. So no, it's not a probability distribution, right? No. This is not 1. However you want to think of that. So that's it. That's a bunch of your questions. Is it a probability distribution? Yes or no? All right. Then we can find the mean, the variance, the standard deviation. of a probability distribution, the mean's pretty easy. You just take each value, whatever value you have, and times it by the probability. So you just times across on your chart and add them up. That's your mean. And we want the mean, or this could be called the expected value. Because if I want to know if like a game is fair, I want to get out that expected value. Okay, so we'll have some examples of some games. Like, what are you expected to get? So, like, if you roll 2 dice and add the results, your expected value should be around 7. So, that's going to be your winningest number. So, that mean or that expected value is really important. And then the standard deviation is kind of an ugly formula, but we'll look at that as we look at some examples. So, here we are. So, first thing is it has to be a probability distribution. So that means these have to add to 1. And I'm 99% sure they do. So 0.008 plus 0.022 plus 0.096 plus 0.282, hopefully I didn't lose my spot, plus 0.235 plus 0.126 plus 0.038 plus 0.001. I must have missed a number. Or I messed it up. So 2, but it has to add to 1. So 235, 288, 1, 2. Oh, I missed the plus 0.192. We're good. It equals 1. It equals 1. So check that. They better add to 1 every time, or you don't do anything with it. So let's start with the mean. Okay. I'm going to do this in red so you can see it pretty well. So we're going to find x and times it by the probability. So basically, I added an extra row, and I'm going to times across. So 0 times anything is 0. 1 times 0.022 is 0.022. And then 2 times 0.096 is 0.192. And then 3 times 0.192 is 0.576. I'm just looking at my notes. So 4 times, this one is 1.128. And let's see, 2, 3, 5, 1.175. And then 0.756, 0.266, 0.08. Oops, 0.008. There we go. All right, so we times to cross, and then now we want to add up this row. Okay, so we're going to add up this row, and I got, we are going to call this our mean. I got 4.123. Okay, and this is also called the expected value. Okay, so that's our expected value. So look over here, and our expected value is around 4, and you can see all the numbers up to 4. These are the higher probabilities here, and then they drop down. So it does look like the average number, right? So the answer should look like the average of those variable, right? That random variable or those values. Okay, so how do I do the variance? If we go back up, it's the standard deviation squared. So we need to find the standard deviation. So it says square the x's and times them by the probability, and then subtract this off here. I think I will open that in StatCrunch and show you that. Give me just a sec. I'm going to open that up. Okay, so I didn't want you to have to watch me type the data in. So here's the data typed into StatCrunch, and I'm on my computer version because it's a little bit easier than the iPad version. But this is a really tricky way to get to that standard deviation. Now we could follow the pattern and solve with the formula. You could, but this is a little easier. I'm going to go to Stat, okay, and I'm going to go to Calculator. and then I'm going to go to custom. So we'll make sure to write this on your notes. So calculator custom. And this is not very easy to think of. Because these are decimals, this is the only way to get them to go in here. So we do X is our values. So those are our values, and our weights are in the probability, and hit compute. The only things it will find, ignore this part. It's basically what are the values less than 4. Here's the mean, here's the standard deviation. Okay, those are the two numbers we can get from this custom calculator. So again, stat calculator custom, and we're able to get to that value. So let's write down what we just found. We found that standard deviation to be 1.485. I probably should have used this symbol, okay, because that means mean of a full population, which we do have, because we have all the possibilities on a distribution. So you should probably use this symbol here. And then if you want the variance, you just square that number. So the only thing StatCrunch will give us is the standard deviation, but I can take and put it into my calculator and square it, and that would give me a variance of 2.205. So a little bit weird ways. So in StatCrunch, we have to go to stat, and then we go to calculator, and then it's custom. Okay, and then you'll be able to get those. So, I mean, the expected value, the mean's pretty easy to get. You'd probably take you longer to type it into StatCrunch than it will to get it. So something like this. Like this would be a good one for like probabilities of an event. So you pay in $5 and the probability of losing is 0.85. You could win $10. The probability of winning the $10 is 10%, and the probability of winning $1,000 is 0.05. So then, like, what's the expected value of this? We're just going to times, right, across, times. Let's do that. So this first one, we're going to do X and times it by this, because I'm way too lazy to type this into StatCrunch. So -5 times 0.85 is -4.25. 10 times 0.1 is 1. And then 0.05 times 1,000 is 50. Okay, add those up. And I get $46.75. Should I play this game if the expected value for me, the winner, is $46? Yeah, I should pay. Totally in my favor, right? Okay, so expected value times across. So let's do one where you come up with your own chart. So pick 5 numbers, 0 through 9 lottery. And you pay $2 for each ticket. If you win, you collect $500. So how many selections are possible? So we have 0 through 9. So that is 10 numbers, and you pick 5 of them. So 10 to the 5th, right? Or you can think of each spot as 10 times 10 times 10, because you could repeat the numbers. So that's 100,000. So there's 100,000 possible ways to get our pick 5 numbers, and the probability of winning would only be 1 out of that 100,000. So this is just from our section before. What is your net profit if you win? So you have to think about what you're making. Well, I paid in $2. They gave me 500, but they didn't give me my $2 back. So your net profit is always what you win minus what you paid in, which is $498. So if you win, you really win $498. So let's use this to get a table going for our expected value. So we're going to think through this as our values of X, then our probability, and then we'll just do the mean on that last chart. So we are either down $2, so always use a negative for that, or we're up $498. Those are our two options. The probability for winning, which is this one, was the 1 over 100,000. What's the probability for losing? You can do 1 minus that probability, right? Or 999, okay, 99, comma, 999 out of 100,000. So we'll definitely have to use our calculator for this one to find that expected value, that mean. I'm going to take -2 times, and then in parentheses, I'll do 99123 divided by 10123. And then I'm going to add it to 498 times 1 divided by 100,000. I kind of did it all in my calculator and didn't put room for it. I think I did 1 0 too many because my answer's off by 1, 1, 2, 3, 4, 5. I did. Okay, so I put it in the calculator. And I got the expected value to be -1.995. So you could do it in, I probably should have done it in parts because this is being weird. Oh, I didn't do a parenthesis there. That's why. All right, I'll just do parts. So you can figure out like this one here is like -19.999998. I got to go out quite a few places. 498 times 1. Use a parenthesis around the 1 divided by the 100,000. And then type it in right. I got 0.00498. So subtract those or add those together. Oh, I should get 19. I think my decimal, no, maybe my answer's just off over here. I got 19 the first time. I thought my decimal was off, but I think I just have the key wrong. So plus that one. Yeah, I get 19.99. So let me erase this. It is one more decimal. I've gotten it 3 times now, so we're going to go with it. -19.99 is our expected value. And so again, we just times across. Well, no, we can't put down -$19. Well, I must have done something wrong. The decimal should be here. So basically, we're down our money, $1.99. If you round it up, you're going to be down your $2. So you're probably not going to win this game. Yeah, I must have just put too many zeros somewhere. 1, 2, 3, 4, 5. Yeah, I'm not sure where I did that wrong. Okay, so make sure you put in your calculator right so you're not frustrated like me. All right, next question. Make a probability distribution of rolling 2 dice and adding the results. So I did a little tree diagram of this one. I copied and pasted. It is a pain for this tree diagram, but I wanted you to visualize when I roll 2 dice and I add them, there's so many gambling games with that, or like Catan or other games that use that 2 dice rolled. But if I roll a 1, I can roll a 1 and get a 2, or I could roll a 2 and add them and get a 3, and so forth. So the high or the lowest number I can ever get is a 2. And the highest number I can ever get is a 6 plus 6 or a 12. And a lot of these repeat themselves. So the 2, there's only one way. But the 3, we can see it shows here and here. And then it drops off because the only way you can get a 3 is a 1 and a 2 or a 2 and a 1. And then a 4 is here, here, and here. A 5 you see in a bunch of places. So 5, 5, 5, 5, and then it drops off and so forth. So let's do a probability distribution of this. I think I'm going to do it just over here, and we'll just go down. So the first number we could get is, we'll do our probability over here, is going to be a 2. That's the lowest we could get. The probability of a 2, if you go 6 times 6, right? That's 6 times 6. There's 36 ways, or add these all up, there's 36 of them, and only one of 36 is a 2. So pretty low probability on that one. Then the 3, there's only 2 out of 36. And then the 4, there's 3 out of 36. The 5, there is 4. out of 36. And the 6 is 5 out of 36. And then the 7 is 6 out of 36. And the 7 is actually the one that happens the most. So 7 happens in each group. So you can see it happens 6 times. Now what happens is, as I get to the 8, it is no longer going to be in this first group. So the 8 is only in these 4. And then the 9's only in these ones, and so forth. So you can see it starts to go back down after the 7. So an 8 is 5 out of 36. The 9 is 4 out of 36. The 10 is 3 out of 36. And the 11 is 2 out of 36. And the last one is 1 out of 36. And that is a full probability distribution of rolling 2 dice and adding your results. Okay, I wanted to make sure to show that distribution because for some reason that one really gets people. Let's